Fine, very good morning to all of you. I'll begin today's session. This will be the concluding session as far as module 1 is concerned. We have come across various power devices. We started off by looking at the power diode, which was a minority carrier device but uncontrollable device. It had only two terminals, anode and cathode. There was only two, the control was not possible because gate or base was not there. That was the first power device, and then we took up the 3 or 4 controllable devices. One was the power BJT, next one was SCR, next one was power MOSFET, and finally IGBT. All the other 4 devices are controllable devices, which means we can decide the instant of conduction, instant at which the device is going to turn on. In some devices, excepting SCR, turn off can also be decided. The moment the gate pulse or the base drive is going to be avoided or is going to be removed, the device will be turned off. Whereas SCR, gate has control during turn on, whereas for turn off, the anode current must be brought down below the holding current value with regards to SCR. So these were the features of various power devices, and then we had come across, for all the power devices, we had come across the structure, steady state VA characteristics, and switching characteristics. This was the mode in which we had discussed various power devices. Now, this session, there are 2 other aspects that involve power devices. One is the snubber circuit, which is the protection circuit. The other one is the gate triggering circuit, which is the control circuitry. So we will deal with control and protection circuit in this session. It will be a very brief thing because nowadays nobody designs a circuit. There are ready-made ICs available for let's say control circuitry, and then for snubber circuit, again it is just a ready-made RC network. So you can straight away pick and choose a snubber, or you can straight away pick and choose a gate drive IC. So I'll just brief you on the control and protection circuit. Okay, so di by dt and dv by dt, they occur during turn on and turn off respectively. Now we need to protect the power device from excess di by dt, which is going to cause hotspot, and excess dv by dt, which is going to cause dielectric breakdown. You need to remember that dv by dt is associated with the, see, remember all are semiconductor devices, so they have particular voltage blocking capability. So excess dv by dt will cause dielectric breakdown. As a result, the device may fail, dielectric breakdown. Whereas di by dt, excess di by dt rather, will result in hotspot, which will lead to thermal runaway problem. Thereby the device is going to be fail. Don't tell bluntly both cases devices are going to fail, but then don't tell bluntly devices fail. You tell what is the sequence, what is the process that is happening due to excess dv by dt and excess di by dt. So that is more important. Now, how do we protect this? Very simple. We know that an inductor is going to oppose sudden change in current, capacitor is going to oppose sudden change in voltage. So we add an inductor in series for protecting against di by dt. We add a capacitor in parallel to protect the device against dv by dt. That's all. Very simple process. But there has to be a small damping resistor because the capacitor is going to discharge. So there has to be a small time constant involved, else the device is going to puncture. So that is the process that happens. As a result, the protection circuit will have, I will draw the snubber circuit. I will take a generic switch. So in case we have a switch here, this is the normal switch. This is going to be put into operation elsewhere. Now, for protecting this switch, we try to add the elements, the snubber elements, which are going to be, I will now add a series inductor, snubber inductor, and then there will be the resistive capacitor snubber, RC snubber. That's all. Very simply RC snubber. So this is going to be LS, this is going to be RS, this will be CS. So effectively, LS is going to protect the device against di by dt. L will take care of that. CS will take care of dv by dt. RS is for slight damping. I hope you might have come across this term damping in control systems. Now, if you don't have this resistance, then the moment the switch is going to be closed, capacitor will discharge. So that will again cause inrush current. That will again damage the switch. Therefore, you need RS. So that is the purpose of damping resistor. That's all. This is the way this number circuit is going to be. Now, how do we decide the values of LS, RS and CS? Design the values of LS, RS and CS. Generally, the snubber inductance, of course, I should write LS, RS and CS. They are snubber elements. Even if I don't write, you will know. Still, for additional clarity, I will write LS, RS, CS. They are the snubber elements. Now, generally, there will be a stray inductance in the circuit, in any circuit for that matter. If you have AC circuit, the source inductance will take care, will play a role, will be the stray inductance. If you have DC circuit, again the stray inductance will be there. Some DC circuits will have an inherent inductor. If you take a boost converter for that matter, that will have an inductor very close to the source. So LS may not be explicitly added onto a circuit. Okay. So generally, when we talk of snubber circuit, only RC snubber is going to be dealt with. So in textbooks, when you come across only RS and CS, again, please understand that the stray inductance is taking care of di by dt. That is the understanding that you need to have. Now, how do we design various elements, that is RS and CS in particular? There are standard expressions. You don't need to worry about them. No matter whether we have a standard expression or not, people don't spend too much time on designing RS and CS. There are fixed RC combinations. They take that and then they start using it. In fact, in our lab, whatever kit is available, I have taken care to open many kits of various power ratings. And then I found that the capacitance will be a standard 0.01 microfarad, and then the RC resistance will be a standard 1 kilo ohm 5 watt resistor. That's all. So that is practice. This is theory. Okay. But anyway, you should know why it is used and how it is designed. Now, I will show you just to make things clear and tell you what is in store for you, the expressions that are used to design these snubber elements. Use them for designing. There may be some simple numerical examples involving design of snubber circuits. That's all. Now, if you take if you look at, yes, I hope it's clear or visible. Now, the design expressions involve inductance will obviously be used to protect di by dt. Now, this is a very simple expression. You know that in the voltage induced across inductor is given by L into di by dt. Maximum voltage has to be impressed across the snubber inductor. Therefore, you rearrange and then you get the inductance value as maximum voltage divided by di by dt. You will know di by dt max and V max. V max depends on the circuit. di by dt max depends on the power circuit, which will be power device, which will be available from the data sheet. This is where reading the data sheet becomes important. My intention was just to tell you how to use the data sheet for practical use. In fact, you will get the data sheet. From the data sheet, you will get this di by dt max. So that is how you design the snubber inductance. And snubber capacitance and resistance, there are various expressions. One is, if you have AC circuit, then there is a thumb rule sort of a thing. So you have 10 VA by VA square 60 by F. And in case of DC circuit, once you know the value of inductance, you can actually calculate the value of capacitance. Okay, for using this expression. R is actually the damping element, which is given by 2 zeta square root of L by CS. Zeta is taken as 0.65, damping factor, damping ratio factor. All right. So this is the way we design. These are the expressions rather to design RLC snubber. Very generic expression. Fine. So this is about snubber circuits. Next comes the gate triggering circuit or protection circuit. Next one is the gate triggering circuit, which is again another important aspect as far as use of power devices are concerned. But then the design is going to be very, very simple. We just need to know what is the power device that we are using, what is the, nowadays people start using MOSFETs and IGBTs, which means threshold voltage, VGS threshold is the important term, and gate source capacitance. You need to charge that gate source capacitance. Depending on how quickly you are going to charge, the device is going to be operated at that particular frequency, that's all. Which means if you operate at megahertz frequency, then your drive circuit should have the power to charge that capacitance. So they are available in the form of ICs. I'll just note down those things or list down those things, and then that would be enough for you as far as handling the devices in practice is concerned. Now, gate triggering circuits. Again, 1R or double R, I still have a doubt. Okay. Now, SCR, I think we had dealt with in the earlier session. If you take SCR, gate triggering is the best one. I think 1R, okay, gate triggering. Now, in gate triggering, there are various methods. One is you can use, the best option is going to be UJT triggering. Something what I had shown you in the single phase semi-converter and single phase full converter. There will be two blue color pulse transformers and there will be a gate control circuitry. That is actually UJT triggering, UJT based triggering. There are other methods also. R method, R triggering, that was the first one that I had demonstrated in lab, and RC triggering, that is also there, but the best one is UJT triggering. Okay. So that is about triggering an SCR. Whereas if you take MOSFETs and IGBTs, there are ready-made ICs which are available, MOSFETs and IGBTs. So ready-made ICs. You need to take care of from the data sheet of, I'll give you some example of gate triggering ICs, gate ICs. Gate triggering ICs include 2110, IR 2110. Of course, this is for triggering a half bridge configuration. Similarly, IR, yes, that is another version. IR 2130 is for three phase. Single phase, sorry, let me be clear. Single phase half bridge. Whereas when you take 2130, this is for three phase bridge, full bridge. Okay. And if you want to trigger only one MOSFET or one IGBT, that is also available. In fact, individual MOSFETs, if you want to trigger, I will write them here. To trigger individual MOSFETs or IGBTs. You can use IR2101. This is used. Students very commonly use this cheap IC, TLP250. That is quite common among students. I haven't used one myself. Actually, it is an opto isolator. If you look into the data sheet of TLP250, it is actually an optical isolator, opto ISO plus gate triggering. This is what students actually use TLP250 for. Very cheap, 100 rupees, and then it works. Whereas 2101, that is quite expensive, 250 rupees. So These are some ICs. Of course, for the past 1.5 years, I haven't used any of them. Therefore, this is what I generally use. There are many other configurations. Of course, all the ICs are from international rectifiers. That is why you get IR. There are ICs from Fairchild Semiconductors, from Texas Instruments. They actually give free samples. You can log into Texas Instruments website and then you can check for MOSFET or IGBT drivers. Texas Instruments. TI. So we can log into TI website so that you get free samples. And remember, when you order for free samples, you take up DIP package, dual inline package, so that the IC will be available in the form of 8-pin or 16-pin DIP package. 8-pin or 16-pin DIP. I hope you know what is called as a DIP. If you do not know what is called as a DIP, then it will be like 4 pins arranged in 2 lines so that you can insert in a breadboard. That is how it will look like. That is called as a dual inline package. There are other packages. Surface mount package is there. SOI, we call it, technically it is called as SOIC package, SSIC package, and then PLIC, plastic leaded IC. So don't take up those things. Please order only DIP package. Okay. So that is about triggering circuit. The objective of triggering IC, I think I told you. The gate source capacitance, anyway, I will write it down as well so that you to remember that, and it is recorded. The objective is to charge the gate source capacitance. I will write CGS. It will be CGE in case of IGBT. Anyway, charge CGS and make sure that VGS, the applied gate source voltage, is greater than the threshold voltage. That's all for turn off. This is the purpose of gate ICs. Okay. Roll off gate ICs. Any triggering circuit does this, but because I have dealt only with ICs, I am writing this.